The valves open, and a ship the length of 3 football fields begins to drown itself on purpose. Not by accident, not because something has gone wrong. Deep inside the hull, seawater is thundering into ballast tanks at a rate that would fill a swimming pool every few seconds, and the crew standing on the working deck are watching the ocean climb up the side toward their boots, willingly. Above them sits a structure the size of a 10-story building. Steel legs the width of oil drums hang beneath it, reaching down toward 4 columns that jut out of the open water like the stumps of a drowned cathedral. And the entire, terrifying point of this operation is to lower that mass of steel down onto those columns while the sea heaves the whole ship up and down beneath it. The gap between the descending legs and the waiting columns is measured in inches. One surge of a rogue wave, one valve that sticks, one miscalculation in the flood rate, and 40,000 tons of steel come down in the wrong place. And there is no crane on Earth big enough to pick it back up and try again. What they're setting down isn't a machine. People live inside it. There are bunks and a galley and a control room with coffee going cold on the desk. There are corridors and stairwells, and an elevator. An elevator that, on the largest of these structures, takes more than 9 minutes to reach the bottom of its shaft. This is a building with a population being installed on top of the sea by deliberately sinking the ship that carried it out. By the time a structure like this leaves land, it is already finished, not a shell. Finished. The processing equipment is bolted down, the wiring is run, the pipes are pressure tested, the living quarters are furnished, and in many cases the whole plant has already been switched on and run through its paces at the quayside. Every hour of work done on shore is an hour that doesn't have to be done later, hanging over freezing water with a helicopter as the only way home. Offshore construction is the most expensive and most dangerous way to build anything human beings build. So, engineers refuse to build there. They assemble the entire structure on land, prove it works on land, and then face the one problem land cannot solve: getting a finished building the size of a city block out to a patch of ocean 100 miles from the nearest shore. Almost no one who watches these things dot the horizon has any idea what it took to put them there. The obvious question, the one that sounds simple until you actually try to answer it, is how you move a fully built, inhabited, building-sized structure across open ocean without it shaking itself to pieces on the way. And beyond that, a harder one. What is the absolute largest thing human beings have ever dared to move this way? The answer to that second question is a structure taller than the Empire State Building, and it did not travel in pieces. But to understand why that was even possible, you have to first accept something that feels wrong. On land, weight is the enemy. Every ton you add is another ton the ground has to hold, another ton the wheels have to overcome, another ton fighting you the entire distance. One of the heaviest single loads ever rolled overland, a gas processing module, ran to several thousand tons, and moving it took hundreds of axle lines of specialized transporters crawling forward at a pace slower than a funeral march. That was near the outer limit of what solid ground will tolerate. Put the same kind of object in water, and the rules invert. At sea, engineers routinely move structures more than 100 times heavier than that overland limit. And they do it because the water itself carries the load. Buoyancy doesn't resist weight. It holds it up. The ocean, the thing that looks like the greatest obstacle imaginable, is the only reason the move can happen at all. The deeper truth of this entire industry is that the sea isn't only the thing you're fighting. The sea is doing the lifting. You're just fighting to control it. But before the water can carry anything, the building has to get off the land and onto the vessel. And the strangeness starts long before anyone reaches open water. A structure weighing tens of thousands of tons does not get craned onto a barge. At that scale, no crane on Earth can lift the thing in one piece. So, instead, it walks. Beneath the completed building sits a carpet of machines called self-propelled modular transporters. Grids of squat hydraulic axles, thousands of wheels acting as one. Each wheel can pivot independently through a full circle. Each can rise or fall on its own to keep the load dead level, even as the ground dips and swells beneath it. Hundreds of these axle lines lock together into a single mechanical platform and the whole assembly, carrying an object the size of an apartment complex, is commanded by one person holding what amounts to a handheld controller. They thumb it forward, and the building creeps toward the water's edge at under 1 mile per hour, slower than you stroll to the kitchen, a pace so gradual you could walk laps around a moving object heavier than a warship. That crawl is not caution for its own sake. It's the only speed at which thousands of tons can be kept from tearing themselves off their own wheels. And once the structure has rolled out onto the waiting barge, it still isn't ready to sail. First, it has to be chained to the ship itself. Crews weld the structure directly to the deck with steel bracing thick enough to survive a storm, a process called sea fastening, because the thing they fear most on the voyage is movement. A building that shifts even slightly on its cradle in a heavy swell becomes a battering ram against the very vessel keeping it afloat. So, it is locked down, immovable, and only then does the barge slip its lines and turn toward open water, dragging a finished building out past the breakwater and into seas that have destroyed far smaller things. Then, at the far end of that voyage, comes the maneuver that opened this story, the ship that sinks itself. They call it the float-over, and it runs backwards to every instinct you have about installing something heavy. You don't lift the building up onto the base. You bring the loaded vessel in until it straddles the pre-installed foundation, its cargo hanging directly above the waiting legs, and then you flood the ship. As the ballast tanks fill, the whole vessel settles lower into the sea, and the building it carries descends with it, inch by inch, until the weight transfers off the ship and onto the foundation. A modern rapid ballast system can carry out that weight transfer for a 20,000-ton structure in about 20 minutes. 20 minutes of controlled flooding, and a building stands where, moments before, there was only open water. The margins that make this survivable are almost cruel in how thin they are. The engineers plan the entire descent around the tide, working inside a window of roughly 3 feet above and below mean sea level, and they deliberately begin as the tide is falling, because the drop of the water buys them precious extra clearance as the legs thread down between the foundation's columns. Get the timing wrong, and the legs foul on the way in. Get it right, and a billion-dollar structure slides into its socket with gaps you could span with your outstretched arms. The people running this are not aiming for a barn door, they're threading a needle in the ocean with a 10-story building. And even in what a sailor would call calm water, the sea will not hold still. A gentle swell, waves that wouldn't trouble a fishing boat, still lifts and drops the barge without pause, which means that as the building descends toward its foundation, it isn't lowering in one smooth motion. It settles and rises, thousands of tons pressing down onto the columns and easing off again with every wave that rolls through. Left uncontrolled, that endless cycle of loading would work the structure and its base against each other until something failed. The defense against it is disarmingly humble, rubber. At the top of each column sits an elastomer pad called a leg mating unit, a shock absorber engineered to a degree that borders on obsessive. It isn't a simple cushion. Each one is a precisely tuned spring that grows stiffer exactly as the load presses harder into it, absorbing the surge of each swell and feeding the building's weight onto the foundation as a controlled squeeze rather than a series of blows. Every unit is custom built for the specific structure it will receive and the specific seas it will face. When engineers set down the topside of the Hebron platform off Newfoundland in 2017, nearly 51,000 tons, the heaviest float-over ever performed, the entire success of the operation rested on lumps of engineered rubber, doing their job in the half-inch spaces where steel met steel. So the building is threaded, cushioned, and set. You would think the hardest part is over. It isn't, because none of this can happen until the ocean grants permission, and the ocean is not generous. These operations live and die by something called the weather window. The mating can only proceed inside a narrow band of wave heights, often no more than 8 to 11 feet, and until the sea drops into that band and stays there, nothing moves. Fleets of vessels worth hundreds of millions of dollars sit at anchor and wait. Not for hours, for days. Sometimes for weeks. Crews watch the forecast the way a surgeon watches a heart monitor, because the moment they commit, they are committed. Through the descent itself, wave rider buoys bob around the site, and motion sensors track the barge across all 6 directions it can move. Pitch, roll, heave, and the rest, measuring every twitch of the vessel against the hard limits the engineers locked in before anyone left port. And here is the nightmare that keeps them staring at the water. If the sea turns mid-operation, the structure can end up frozen half installed. Not on the ship anymore, not yet on the foundation either. Suspended in the most vulnerable state it will ever occupy, waiting, while the weather does whatever it intends to do, for the sea to calm enough to finish what was started. There is no fast exit from that position. There is only the wait and the hope that the forecast held. That is how you put a building onto the sea. But installing one is only half the story, because these platforms are not permanent. The oil and gas fields beneath them run dry after decades, and when they do, every structure has to come back off. For most of the industry's history, taking one down meant sending crews out to cut it apart by hand, piece by piece, hundreds of feet above the waves. A slow, grinding demolition that could take dozens of separate lifts and keep workers exposed over open water for months. To put an end to that, one company built the largest and most powerful vessel ever to float, measured by the sheer weight of water it shoves aside. Its slot alone is 400 feet long. The ship is a twin-hulled giant with a split bow, a vast gap carved down its front end so it can drive straight at a standing platform and swallow it whole between the two hulls. It is a floating town in its own right, well over 1,000 feet from end to end, with berths for more than 500 people who live aboard while it works. Once a platform sits inside that slot, the vessel performs the float over in reverse, pumping out its ballast, rising in the water, pressing lifting beams up under the topside until the structure's entire weight comes off its legs and onto the ship. In a single operation, it can take up between 48 and 60,000 tons. And the reason it can do what no crane can becomes clear the instant a lift begins in open water. As the sea rolls the hull, a system of active motion compensation drives the lifting beams in the opposite direction, holding them nearly still relative to the platform they're gripping, so that even as the deck heaves beneath the crew's feet, the point where steel meets steel barely moves. Engineers found that without it, even small waves could hammer damage into a structure this heavy. With it, the ship can work in seas that would make the lift impossible any other way. Most of that lift is slow and deliberate. The final part is not. Once the beams have taken up the bulk of the load, a fast lift system driven by high-pressure compressed air drives the entire structure upward, around 6 feet, in roughly 15 seconds, while 11,000 tons of water dump out of quick-drop tanks to throw the ship higher still. One coordinated heave, and a structure the size of a building breaks free of the foundation it stood on for decades. When this vessel pulled Shell's Brent Delta platform off its base, 24,000 tons gone in a single lift, it was carrying out a maneuver that reportedly cost around $3 billion just to make possible. A ship built for the sole purpose of lifting platforms whole and carrying them home. Which leaves the one structure this entire story has been circling without naming. The tallest object human beings have ever moved across the face of the earth. It stands about 1,550 feet tall, taller than the Empire State Building, and it did not travel in pieces. Norway's Troll. A platform was assembled whole in a sheltered fjord, and then floated out into the open sea as a single structure. With a total weight of around 1.2 million tons under tow, it remains the heaviest object humanity has ever relocated, and the tallest ever moved from one position to another relative to the surface of the planet. To grasp what was floated out of that fjord, you have to understand how it was built. Trolle's legs were formed from reinforced concrete poured in one continuous, unbroken operation, crews working around the clock so the concrete never set into seams, because a single cold joint could have become a fault line under the crushing pressure of the deep. The walls of those legs run more than 3 feet thick. The base swallowed close to 250,000 cubic yards of concrete, and the whole colossus could float for a single reason. It is, in essence, a hollow concrete iceberg. Its base is built as 19 sealed cylindrical cells, and those hollow voids give the giant its buoyancy, so most of the structure rides beneath the waterline as it moves, exactly like the ice mountains it resembles. A city block of concrete drifting across the North Sea, held up by nothing but trapped air and the water it displaces. That drift took 7 days. A fleet of tugs strained against a structure that could not be stopped quickly, could not be turned quickly, and could not, under any circumstances, be dropped. Every mile was a mile that could not be taken back. There was no dock to return to, no way to lift it if something went wrong. only slow, relentless forward progress across 125 miles of open water, with the tallest thing humanity had ever moved swaying gently at the end of the tow lines. And then, at the destination, they killed its buoyancy on purpose. The same cells that let it float were flooded, and the tallest object mankind ever moved began to sink, controlled, deliberate, down through nearly 1,000 feet of water until its base struck the seabed. There were no anchors, no cables driven into rock. A structure like this needs none. Concrete skirts beneath its base drove roughly 120 feet down into the seafloor, and its own staggering weight has pinned it in place ever since, held by gravity alone, requiring no mooring of any kind. A structure that floated across an ocean, then was ordered to sink and became a permanent piece of the planet. Inside one of those towering concrete legs runs the elevator from the beginning of this story, the 9-minute descent from the deck above the waves down toward the sea floor. And in 2006, in the strangest footnote this field has ever produced, that hollow leg was turned into a concert hall. A singer named Katie Melua rode down into the shaft of the tallest object ever moved by human beings and performed nearly 1,000 feet beneath the surface of the sea. The deepest concert ever held, staged inside the hollow bones of a building that was floated across the ocean and sunk into the world on purpose.